And we are back. Hi. Now, anyways, so welcome back, guys. We are now moving on to uniform motion problems. Okay, two more examples and we're done. All right. So let's check this out. Uniform motion problems are problems where the object moves at a certain speed or rate. Okay. So it's the idea of taking something that is in motion, something that is moving, and you know how something can move fast and then slow and then fast again, you know, different speeds. It's the idea of, well, what if we looked at the whole trip? What would it look like if they were moving the same speed throughout? Same speed throughout. Okay. Anyways, you're bored. You want this done. Let's go. So we're looking at distance. Distance traveled, rate times time. We've been using this a lot. I'm asking you to remember this. This is something you should know. Okay? We normally see this as D equals RT. D equals rate times time. This is something we're going to be looking for. Are you ready? Are you ready? We're going to use it. Are you ready? Yeah. Let's use it. So, Nita took a non-stop flight. So she's flying from somewhere to see her grandma. Aww. It's a 750-mile trip, and it takes 3 hours and 45 minutes. That's fun. Then, on her way back, because of bad weather, right here, because of bad weather, the return trip, going back home took 4 hours and 45 minutes. Yikes. What was her average speed in miles per hour for the round trip? So let's take a moment to think about this. Think for a moment. She has to travel 750 miles both ways. On the way over, 750 miles, does it in 3 hours and 45 minutes. Then, on the return, she goes 745 miles again, but this time it takes longer, 4 hours and 45 minutes. Going there was faster, coming back, slower. But we're looking at the average speed, okay? So that means it's going to be a speed between her going time and her returning time, right? Between going there and back, it's going to be a speed that's in between the both of them. Does that make sense so far? Let's check this out. So first, to have everything uniform, we need to change minutes into hours. And you're like, well, why do we need to do that? Okay, first of all, it's really hard to write 3 hours and 45 minutes in a math problem. You either need to write everything in minutes, okay, everything in minutes, or everything in hours. You gotta pick one. I'm picking for you. We're using hours here, okay? The reason we use hours is because we're probably gonna measure the speed in miles per hour. Got it? Thinking ahead. That's half the battle. So, we've already done conversions. You're used to this. 45 minutes times 1 hour over 60 minutes. That's our conversion factor for hours to minutes. Will give us 0.75 hours. That means our going time is 3.75 hours because 3 hours and 0.7 hours. And return time is 4 hours, 4.75 hours. Got it? Cool. Moving forward. So now that we have the times, it's time to figure out what is our average speed. Well, the way we do this is by taking our distance equals rate times time formula and working with it. So let's find this average speed. So first we want to work with our formula. Distance equals rate times time. We want to change this thing. We want to change this bad boy right here. We've got to change it. How are we going to change it? We want to know what the speed is, average speed. That is going to be R. D is distance, T is time, R is our rate or our speed here. So let's go find it. Divide both sides by T or multiply by 1 over T. Doesn't matter. Same difference. You're going to get D over T equals R. I'm going to flip it around. This is what we're going to be using for our average speed. Now, average speed is calculated by using total distance. The total distance going forward and back. Forward and back. Okay? Total trip. total distance divided by total time of the trip. Okay, if you look at the book, it's going to show you something that's very different and time consuming. You can use that. The book is correct, but this is faster. And I know how much you guys appreciate faster, so here's the faster way. Okay, so let's find our total distance. Our total distance, let me get out of the way here. Our total distance is 750 both ways, so that's 750 twice. Add it together. Total distance. Our times, we already found those. Add those together. I did not add those together. That's what you need to do. So I want you to add these together and divide that total distance by the total time. I'm going to post a question for it. Answer it. And hopefully, the answer that you've given me is 176.5 miles per hour. Taking that total distance dividing by total time, this is what we get. So she traveled pretty fast. Okay, that was pretty good. But that's the average trip. She was faster at some parts, going over to her grandmother's, and slower on others, returning home. Does that make sense? Alright, good. Here we go. Time for a problem for you. Let's see how you guys do with this one. So I'm putting up the average speed equals total distance over total time for you. But I want you to handle the rest of this. I'm going to disappear. And let's see how you handle it. To solve this problem, we should recognize that the total trip here is 15 miles both ways. That's 15 plus 15. For total time, we're going to change this into hours since our answers over here are miles per hour. So we should have 15 plus 15 for total distance and 0.5 plus 0.75 for our hour times. Together, that makes an answer of 24 miles per hour. Let's move on to the last example. Now, the last example is going to be a bit complicated. I mean it. It's going to be complicated. Seriously. Focus. It's a lot of words, but it's not that crazy. I promise. Ready? So let's check it out. It's going to work just like the first two problems from part 1. A railroad operator is sitting there and he discovers that two trains are heading toward each other. They're going to crash! Except that he notices this while they're still really far away from his control panel. He's looking at the computer. He's like, oh my gosh, they're going to collide if they stay here. Oh my gosh, I got to warn them. Does he have the time to warn them? Let's find out. So he knows currently, when he discovers this problem, the trains are 53 miles apart from each other. They're 53 miles apart. Okay, that's good. That's good, but trains travel fast. One train is traveling 75 miles per hour. Oh my gosh. They're going to collide in less than an hour then, because that one's traveling at 75 miles per hour this way. And the other one's traveling at 40 miles per hour. Oh my gosh. So, the faster train, the faster one, will require 5 miles to stop. It's going so fast, it needs to stop over 5 miles. And the slower train needs 3 miles to stop. Okay, so if we can give them the stopping distances, how many minutes does the operator have to warn them? Let's find out. Let's see if we can save the trains. Save the trains. Save the world. Okay, so let's start. First, we want to draw a diagram. It's kind of helpful. So we know that we've got all this stuff. These two trains are 53 miles apart. It takes 5 miles to stop, and for the faster train, and it takes 3 miles to stop for the slower train. And we know they're 53 miles apart. Now, if we account for them stopping safely, okay, we need to remove that as part of our distance, okay, right? Because we need to assume that they're going to get the 5 miles and the 3 miles they need to stop. So that means that we have to think of this with 8 less miles. 53 minus our 5 and 3 for 45 miles. So we need to figure out how much time we've got before they cover those 45 miles, right? How much time do we have to wait So that way, then we tell them, okay, so break, and then they break, and they just like touch each other just like that. Okay? So, that's what we're focusing on. Are you with me so far? Hopefully. If not, click back, rewatch this part. Two trains coming together, and we're trying to figure out what is the last time that you can tell them to stop so that way they just screech to a halt. No, they're not kissing. Okay. So, now that we have done that, now we want to start building a table like we did last time. Boo. So, let's let H be the number of hours the operator has to warn them. Okay? H be the number of hours, right? Since they're traveling in miles per hour, we should probably measure time in hours. Let's also think about what we know about the trains. What do you know? What are some important things that we know about these trains? We should know things about the speed, time, and distance. The three things necessary for the distance formula. D equals RT. So, let's together make another table. So, notice this time we have the fast train versus the slower train, the other train. We look at their rates. The faster one is at 75 miles per hour, the slower one's at 40 miles per hour. Then we have time. We know that they both have the same amount of time that we're looking at, the same amount of time, so that way we can tell them to stop right before they collide. Alright? Then, the last part, we need to put it together in the formula so we know that distance, the distances that they will be covering, are equal to the rate times the time. So that's what we do. Rate times time. Rate times time. Okay? And this is where it becomes just like the first couple problems. We are going to add these together. Uh-oh, don't know where my mouse went. There it is. We're going to add these together, and that's going to equal the amount of distance they have to cover before they crash, which is 45 miles. So let's put that together. The distance traveled by the fast train plus the distance traveled by the other train should equal the 45 miles it takes for them to collide, come together right before they collide. You guys ready? Solve it. So, add together, divide, and we find 0.39 hours. Perfect. I love when I have 0.39 hours, don't you? Yeah, what's 3.9 hours? Turn it into minutes, please. Let's multiply by 60. Let's use a conversion here. This is 23.4 minutes. That conductor has about just a little bit over 20 minutes to let these trains know, oh my gosh, you're going to crash. You need to slow down, you need to stop, we need to switch tracks, whatever. Got it? Cool. And that's that. I have one last problem for you guys to work with. Okay? So I'm going to move my face down here. Two students are traveling on their bikes. Instead of coming toward each other, they're going away from each other. One is faster. The one heading south goes 17 miles per hour. The other one goes 15 miles per hour. About how many miles will they, or how many minutes will it take for them to get 7.5 miles apart? I want you to figure out the rest of this. And we're back. So, hopefully you made this equation. This equation based upon the speed of the first kid times the time it's going to take for him to bike, plus the speed of the second kid times the time it makes for him to bike. This is two distances, distances plus distances, and we want them to keep going until their distances are 7.5 miles apart. And that's how we get that. His distance plus his distance should total a total distance traveled of 7.5. You solve, and you should get 2.34 hours. Multiply by 60, and you'll find our answer was indeed 14 minutes. Thank you guys, you've been a wonderful audience. Thank you for participating in this, and I will see you on Monday. Hopefully you have questions for me, and we'll practice, and we'll be ready for that test. Bye-bye.